All right, let's move on with section 3.4, which deals with naming binary ionic compounds. And a binary compound, as the name suggests, is a compound that is made up of two different elements. And the way that we name a binary ionic compound is first by listing the metal. So the metal always comes first in the compound. And then we add the nonmetal stem, plus we add the suffix "ide" at the end. So an example would be something like sodium and chlorine coming together, as you see over here. So we have sodium metal and we have chlorine gas. They come together to make NaCl. So we list the name of the metal, and the metal in this case is sodium, Na, right? So we just put sodium, okay? And the stem of chlorine is going to be chlor, and then we add the suffix "ide" at the end, and that's where we get the name sodium chloride. Now the thing is that sodium is a group 1 metal, and so sodium can only have one charge. Sodium is always +1. Whereas sometimes you get metals like copper, for example. It says compounds with metals that can form more than one type of ion must indicate which ion is present by a Roman numeral in parentheses following the name. If you look in the textbook, there's a table. It's table 3.2. It's not in my slides, but I want you to take a look at that table because it'll show you that most of the transition metals are capable of adopting more than one charge. And so you would have to name this compound copper 2 chloride. Now, if you're wondering, well, how do I know it's copper 2 chloride? Well, the way you're going to know that is that chlorine, or chloride rather, is always -1. But there's two chlorides, right? So -1 times 2 gives you -2. Well, what must the charge of our copper be? It has to be +2, like this. So we say copper 2 chloride, and the 2 with the Roman numerals, that means +2. We call this the stock nomenclature system. So if you've Googled this and you've heard of the stock naming system, that's what it means when we use Roman numerals. It's the stock nomenclature system. So let's say, for example, you had Cu, I can do that a little neater. Let's say you had CuCl. Well, again, chloride is always -1, but there's only one of them. So that means that the charge of your copper would have to be +1 to make the ionic compound neutral. And so this compound, CuCl, would be copper 1 chloride. Okay? So again, the only time we incorporate these Roman numerals are with transition metals. And there are some exceptions to that, like silver and zinc, for example. Silver is always +1, zinc is always +2, but most transition metals can adopt more than one formal charge. So these are the stems, and so when you have your nonmetals, after your metals in an ionic compound, if your nonmetal is bromine, you're going to use bromide as the representation of bromines, or the bromide ion, I should say. So we have bromide, chloride, fluoride, iodide, nitride, oxide, phosphide, and sulfide. Okay, so you have to get used to these stem names, as well as always adding the suffix IDE. So right, you're going to add here IDE, and so you get bromide, chloride, fluoride, etc., etc. Also, it's a good idea to memorize the charges. So bromide is always -1, chloride is always -1, fluoride is always -1, iodide is always -1. Then you have nitride and phosphide. Nitrogen and phosphorus are both in the same group, and so they're both 3-. And then oxide and sulfide, again, oxygen and sulfur are both in the same group, and so they're always -2. All right, the following examples include ionic compounds and ions that can be combined to form binary ionic compounds. In each case, name either the compound provided or the compound formed from the electrostatic attraction of ions. So the first one, we have potassium. So we have potassium and chlorine. So this is going to be chloride. So this is potassium chloride. Okay, and no Roman numerals are required because potassium is in group 1. It's not a transition metal. The next one, we have strontium and we have oxygen. So we're going to name this compound strontium oxide. Okay, I'm just putting the oxide below because I don't want to run out of space here. So oxide, strontium oxide. The next one is chromium, and a chromium 2 ion and a sulfide ion. So since we have positive 2 and negative 2, they're going to come together in a 1-to-1 ratio to balance out the charges. But keep in mind chromium, if you look at table 3.2, you'll see that chromium is in there and that it can adopt more than one charge. You see chromium is over here as well. So the first one, we're going to make CRS, right? A 1-to-1 ratio of chromium and sulfur. And this is going to be chromium 2 sulfide. And the last one, to make a compound out of chromium 3 and a sulfide ion, keep in mind you want to cross the 3 and the 2, so you end up with Cr2S3. So this would be chromium 3 sulfide. So chromium 3 sulfide. All right, now let's turn our attention to covalent bonding. So if you've ever taken a biology class and studied things like proteins, peptides, lipids, DNA, those molecules are all held, or big molecules, but they're all held together through a covalent bond. So let's get into covalent bonding. Now we saw that ionic compounds, just to summarize, ionic compounds were when we had a metal and a non-metal combined, okay? But when we're talking about covalent compounds, we're talking about non-metals only. So non-metals only. And if you're wondering, well, what would be an example of a compound that has just non-metals? Well, what about CO2, carbon dioxide? Carbon isn't a metal and neither is oxygen, right? What about water, H2O? Hydrogen isn't a metal, neither is oxygen, okay? So there's lots and lots of examples of molecules that are held together by covalent bonds. So the question they're posing here is, how do nonmetals, which cannot easily gain or lose electrons, form chemical bonds? Well, the answer is, when you have nonmetals bound together, they must be held together by covalent bonds. So covalent compounds are compounds that are formed when two what? Nonmetals share electrons, okay, to form a chemical bond. Now you remember that with ionic compounds, the electrons are actually transferred, so you had a cation and an anion, but with covalent bonding, this is not the case. They're actually sharing the electrons. And you can see here in figure 3.11, carbon atoms along with hydrogen, oxygen, nitrogen, and phosphorus are bonded to make up the DNA double helix. And so later on when we get into organic chemistry, we're going to focus a lot on elements like carbon, nitrogen, oxygen, hydrogen, right? Phosphorus, sulfur. These elements are going to make up more than 95% of what we're going to deal with in the section on organic chemistry and biochemistry. Now, what about molecular formulas and Lewis structure? So let's unpack this here. A molecular formula is a representation of the molecule of a covalent compound consisting of the symbols of the elements followed by subscripts describing the number of each atom following the elemental symbols. We can go right back to the previous slide and use an example like CO2, right? There's no subscript next to the carbon. There's nothing here. There's no number. So it implies there's only one carbon, but there's two oxygens in CO2. That's a molecular formula. H2O, right? The subscript 2 implies there's two hydrogens. The no subscript after oxygen implies there's only one oxygen. So two hydrogens and one oxygen come together to make water. Another good example would be something like NH3. That's ammonia. Okay, it's found in household cleaners like Windex. It has one nitrogen and three hydrogens. Another example that we're going to look at later on would be something like C2H2. This is acetylene. If you've ever used an acetylene torch for cutting metal, two carbons and two hydrogens combined together to make acetylene. Another example, and this is going over to the one that's shown here, would be fluorine, a molecule of fluorine. So if two fluorine atoms join together in a single bond, if they share a pair of electrons, you get a fluorine molecule like you see right here. But that would be the molecular formula, just F2. Whereas a Lewis structure is a diagram that shows the bonding between atoms of a molecule and non-bonding pairs of electrons that exist in molecules. And so you see that right here with F2. This is our fluorine molecule, but this is a Lewis structure. So this is a Lewis, not Lewis, getting ahead of myself here, Lewis structure, okay, of fluorine. And you can see that there's a line between the two fluorines, and this represents a shared pair of electrons. Keep in mind the word pair means two electrons. And then all these pairs here, we call these lone pairs. You can see that in the fluorine molecule, there's a total of 6 lone pairs in here. Anyhow, I'll get rid of that. And there's one shared pair between the two fluorines. So again, what is a lone pair? They're pairs of electrons that are non-bonding, and they serve to depict the completion of the atom's octet. All right, how do we draw Lewis structures? Well, in these slides and in your textbook, there's a formula that I show you here that's a stepwise formula for drawing Lewis structures, and that's great. There's nothing wrong with following these steps that I'm going to present to you in this video. In fact, you should. However, when it comes to drawing Lewis structures, there's only one way to get good at it, and it's like just about everything in chemistry, and that is starts with P, ends with ractus. That's right, practice. You have to practice drawing Lewis structures in order to master drawing Lewis structures. So step 1 is going to be determine the number of atoms of each kind in the molecule from the molecular formula. So do we have 1 carbon? Do we have 2 carbons? Do we have 2 hydrogens, 4 hydrogens, etc.? Determine the total number of valence shell electrons contained in the atoms of the molecule. Well, look, if you're like, well, how am I going to tally all that up so quickly? Well, we're only going to be drawing Lewis structures for elements that you see on here. Okay, so you see groups 1, 2, 13, 14, 15, 16, and 17. Well, I can make this really easy for you, okay? Any element in group number 1 is going to have 1 valence electron. Anything in group 2 is going to have 2 valence electrons. Anything in group 13, you guessed it, 3, 4 electrons, 5 electrons, 6 electrons, and 7 electrons, okay? So if you wanted to draw the Lewis structure of oxygen, for example, it has 6 valence electrons, so 1, 2, 3, 4, 5, 6. Right? If you wanted to draw the Lewis structure of carbon, it has 4 valence electrons, so you'd put 1, 2, 3, 4, like this. Okay, so that's pretty straightforward. Step 3, arrange the molecule with the least electronegative atom in the center, the middle, and the more electronegative atoms and hydrogen on the outside. Well, if you're wondering, how do I determine the electronegativity? Well, you remember from earlier on in this class, the pattern that we learned is that electronegativity increases going to the right and up, right? You can see here that fluorine is the most electronegative element in the periodic table, and it decreases from there. So again, going back to step 3, we're going to put the least electronegative atom in the middle, unless it's hydrogen. Hydrogen can never be in the middle. Why? Because hydrogen can only ever form 1 bond. Right? Hydrogen can only form 1 bond and it has no lone pairs. And the reason why is because its electron configuration is 1s1. Okay? It only has an s orbital available to it. All right, step 4, connect all the atoms in the initial structure by single covalent bond. Use the remaining electrons to complete the octets of all atoms in the structure. Start with exterior atoms and add electrons to the central atom last. Remember, hydrogen atoms require only 1 pair of electrons to achieve the noble gas configuration of helium. Look, if you like shortcuts, and I do, okay, there's nothing wrong with a shortcut or, a little trick to make things go a little faster. Look, a shortcut you can use in this class is hydrogen will only ever have 1 bond, no exceptions to that rule. If you find an exception to that, somebody did something wrong, okay? The other one would be, if you've got a good memory, fluorine always has 1 bond and 3 lone pairs, okay? Again, there's no exceptions to these 2 that I've just drawn. Hydrogen, 1 bond, no lone pairs. Fluorine, 1 bond and 3 lone pairs, always, always, always. Number 5, if all octets can't be satisfied with available electrons, move non-bonding pairs, meaning lone pairs, to positions between bonded atoms to complete octets. This will sometimes create double bonds and triple bonds. There's no such thing as a quadruple bond, but making a double bond is not a problem, okay? It says here double bonds, the covalent bonds resulting from the sharing of 2 pairs of electrons. So if you have, 2 elements and they have a double bond like this, right? You have 2 electrons in this bond and 2 electrons in that bond. Anyhow, I'll just erase that since it's not really a molecule. And then a triple bond is the same rationale. 3 bonds between two atoms means you're sharing 3 pairs of electrons. Remember, every bond represents 2 shared electrons. So if you have a double bond, that's 4 shared electrons. And if you have a triple bond, it's 3 shared electrons. All right, here's some examples of covalent bonding. This is pretty small here, so you're gonna have to bear with me as I zoom in here. But we have nitrogen gas, and you can see the Lewis dot structure of it over here. They gave you the Lewis dot structure of CO2, of formaldehyde, of methane, of ammonia, water, and oxygen difluoride, okay? There's quite a bit of information on here, but I'd rather get into practicing drawing some covalently bound molecules. Okay, so example 3.7, draw Lewis structures for the following molecules. Okay, here's how you're gonna do it. And remember, you need to practice this a lot to get good at it, okay? So we're gonna start with NH3. How do we draw the Lewis structure of ammonia? So I'm gonna rewrite it here. And how many valence electrons does nitrogen have? Well, nitrogen has 5 valence electrons. How many valence electrons does hydrogen have? It has 1 valence electron. If you're staring at the screen and saying, where did you get that from? Remember, if I scroll back here, hydrogen is in group 1. It has 1 valence electron. Okay? Nitrogen is in group 15. It has 5 valence electrons. Remember, you're always going to have a periodic table at your disposal, and you should be using one as you work through these problems. So we've got 5 plus 1, but there's not 1 hydrogen. There are 3 hydrogens, so times 3 like this, so that gives us a total of 8 valence electrons. Well, the rule was put the least electronegative element in the center, except for hydrogen. Hydrogen can never be in the center. So what does that leave us with? The only possibility is to have the nitrogen in the center. So we'll put our nitrogen here, and we're going to start by drawing a bond to each one of the hydrogens. Now, how many electrons have I used up at this point? I've used up, remember, every bond has 2 electrons. 1, 2, 3, 4, 5, 6. Okay, remember, hydrogen can only have 1 bond. So all of the hydrogens are satisfied. They can only have 1 bond and no lone pairs. But what about the nitrogen? Does it have an octet? Is it surrounded by 8 electrons? No, it's surrounded by 6 electrons. And there's 2 electrons left over, so where should they go? They should go on the nitrogen like this. Now, does the nitrogen have a complete octet? Meaning, is it surrounded by 8 electrons? 1, 2, 3, 4, 5, 6, 7, 8. Yes, it is. So this would be the Lewis structure of ammonia. If we take a look at C2H2, let's go a little faster here. Carbon has how many valence electrons? It has 4, but there's 2 carbons. Hydrogen has 1 valence electron, but there's 2 of those, so that gives you 8 plus 2, which gives you a total of 10 electrons. Well, we know that hydrogen can only have 1 bond, right? Hydrogen can only have 1 bond, and just by process of elimination, the only way this could work is if we had the 2 carbons bound together, and then we have each hydrogen with 1 bond like this. So now both of the hydrogens are happy, but how many electrons have we used up? We've used up 1, 2, 3, 4, 5, 6 electrons like this. We still have 4 electrons left. Well, remember, hydrogen only ever has 1 bond, so where are we going to put the other 4 electrons? Well, ask yourself, do the carbons have complete octets? Let's just focus on this one I have in the yellow circle. It's surrounded by 1, 2, 3, 4 electrons. That means it needs 4 more. So how am I going to satisfy this? Well, the only way to do it is to put 2 more bonds between the carbons like this. Now, with this triple bond, both carbons are surrounded by an octet. Remember, these electrons are shared. Okay, these are shared electrons. So that means this carbon gets the benefit of it, and this carbon gets the benefit of them. So if I just look at this carbon here, for example, it's surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. What about this carbon? It's surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. So both carbons have a complete octet, and there you have it. So this molecule, again, is ammonia, and this molecule here is acetylene. All right, so if you have a great memory, which I know a lot of you do, better than mine, you can probably memorize a lot of these structures, because things like ammonia, carbon dioxide, methane, these are molecules that come up constantly in chemistry class. Next, you have to learn how to calculate what's called formal charge. So calculating formal charge. Question, when we're drawing a Lewis structure, how can we be certain that we are placing electrons in the right place? And the answer is formal charge. The way you calculate formal charge is, the way they lay it out in the textbook is like this. Formal charge, the way it's calculated is you take the number of valence electrons on your atom, you subtract the number of bonds, and then you subtract the number of lone pair electrons, okay? I have an easier way to do it. Mr. Dion's way of doing it is this. Formal charge is going to be equal to the number of valence electrons. So it's the same so far. Then we're going to subtract the number of sticks, and we're going to subtract the number of dots, okay? So a stick is a bond, and a dot is just an unpaired electron. So compounds are most stable when the formal charge is minimized. So preferably a formal charge of 0, but formal charges help explain exceptions to the octet rule. So let's take a look at this molecule over here. This ion. This is called a cyanate ion, okay? But if you want to calculate the formal charge, let's just run over a few of them very quickly. Oxygen has 6 valence electrons. It's got 2 sticks attached to it, minus 1, 2, 3, 4 dots, which gives you 0. So we have no charge on the oxygen, right? Now if we go to the carbon, we say carbon has 4 valence electrons minus 4 sticks minus 0 dots gives you 0. So there's no charge on the carbon. But what about the nitrogen? Well, you can see there's a -1 above it. Nitrogen has 5 valence electrons, subtract 1, 2 sticks, subtract 1, 2, 3, 4 dots. Well, 5 minus 6 gives you -1. All right, and we do the same thing for the other ones. And you can see that in the first 2 Lewis structures here, you can see that they both have a -1 on an atom. In one of them, it's in a nitrogen. On the other one, it's in an oxygen. But you see this last Lewis structure here. This Lewis structure, I would say, is not really pertinent because you're adding extra charges for nothing. Okay, you have a -2 and a +1. But you should practice and make sure you understand where that -2 came from. 5 valence electrons for nitrogen. Subtract 1 stick, subtract 1, 2, 3, 4, 5, 6. So if we take 5 minus 1 minus, 6 gives you -2. Okay, so you can practice calculating your formal charge that way. And remember, compounds are most stable when? They're going to be most stable when the number of atoms with formal charges is minimized. So you can see that these two, there's only one formal charge, but in this one, you have 2 formal charges. And so the 2 first Lewis structures are going to be more pertinent than the last one. All right, draw Lewis structures for the following molecules. Let's do it. So the first one is BH3. This molecule has a name. It's called borane. Okay. You might think, oh, I'll call it boron trihydride. You could, but it's technically called borane. Boron has 3 valence electrons. Hydrogen has 1, and there's 3 of them, so that's a total of 6 valence electrons. So we have our boron in the center. Remember, hydrogen can never be in the center. It can only have 1 bond. So 1, 2, 3, 4, 5, 6. So like this, we've used up all of the electrons. So you can see that boron doesn't have a complete octet. It's only surrounded by 1, 2, 3, 4, 5, 6 electrons, but that's all we have to work with in this case. And it's okay because boron only has 3 valence electrons, right? Because boron's electron configuration is 1s2, 2s2, 2p1. So it only has a total of 3 valence electrons. So it can only form 3 bonds anyway, if you want to memorize that. The next one, sulfur trioxide. So for sulfur trioxide, sulfur has 6 valence electrons, and so does oxygen, but there's 3 of those. So we get a total of 24 valence electrons. Well, if you look at sulfur and oxygen is above sulfur in the periodic table, and so based on electronegativity, oxygen is more electronegative than sulfur, so the sulfur is going to be in the middle. So let's start by connecting each one of the oxygens, and then we'll fill up the octets of the oxygens like this. Okay, so now that we've done that, we've used up a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So you can see that we've used up we have used up all of the electrons, and you can see that each one of the oxygens is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. However, the sulfur is not surrounded by 8 electrons. It's only surrounded by 1, 2, 3, 4, 5, 6. So how are we going to mitigate that? Well, we could start by taking one of the lone pairs. I'll just erase this one here, and we could make a double bond like that. So now our sulfur is surrounded by 1, 2, 3, 4, 5, 6 electrons like this. You might think we're done here with our Lewis structure, but the problem with this Lewis structure is that now the two oxygens excuse me, have a formal charge of -1 each, and the sulfur has a formal charge of +2. And we want to avoid having formal charges because you see that -2 and +2 cancel each other out. And so the way we're going to do that, I'm going to redraw it just so I leave this on the screen. The way we're going to draw sulfur trioxide is actually like this. And you might be saying, well, sulfur is surrounded by a total of 12 electrons now, which exceeds an octet. That's true, but if you have an element that's in the third period or beyond, third period, it can exceed an octet. That's okay. And so this would be a more proper Lewis structure. Why? Because the formal charge of every atom, all the oxygens are 0, and the sulfur is 0 as well. So here's a slide you might need to meditate on for a little while. I remember learning this, years ago, and always, at the beginning of chemistry, I was kind of struggling with the idea of molecules versus compounds, covalent compounds versus ionic compounds. There's nothing wrong with saying covalent compound. There's nothing wrong with saying covalent molecule. There's nothing wrong with saying ionic compound, but there's no such thing as an ionic, so don't write this down, I'm probably committing a crime of some sort here, but there's no such thing as an ionic molecule, okay? That doesn't exist. Ionic species can only be referred to as compounds because molecules are held together with covalent bonds, okay? So you see here we have water in the first one, which is a molecule, and then we have sodium chloride over here, which is an ionic compound. So water is covalent because hydrogen and oxygen are both nonmetals, whereas sodium chloride is ionic because sodium is a metal and chlorine is a nonmetal. So covalent bonds form discrete molecules, individual water molecules, for example, whereas ionic bonds form an organized crystal lattice where they're all clustered together, as you can see here in this cube, okay? Molecular weight is the sum of the atomic weights of the elements in the molecular formula of a compound. For example, let's say I wanted to calculate the molecular weight of water, for example. Okay, so I'll highlight it in yellow here. Well, just approximately, water has an atomic weight, hydrogen has an atomic mass of about 1.01 atomic mass units, and there's 2 hydrogens. And then oxygen is about 16.00 atomic mass units. So when you put those all together, you get 18.02 atomic mass units, and that would be the molecular weight of water, okay? You could practice it if you were to try carbon dioxide. I'm kind of running out of space here, but CO2 has a molecular weight of around, it's a little bit more than 44 atomic mass units if you want to practice that, right? You've got 1 carbon, which is 12, 2 oxygens, which are 16, so that gives you around 44. Well, I guess I spoke too soon because I just calculated the molecular weight of CO2 on the last one. So CO2, so we have 1 carbon, which is a mass of 12.01 AMU, and then we have oxygen, which has a mass of 16.00 AMU, but there's 2 of those, so that gives you 32 plus 12.01, so that gives you 44.01 AMU. But another one you could try on your own would be glucose. So glucose has a formula that's C6H12O6. So you've got 12 carbons, 6 carbons, 12 hydrogens, and 6 oxygens. You tally that all up, and it should be close to 180 AMU. So you could practice that one on your own time, right? 12 times 6 plus 12 plus 16 times 6.